All right, guys, I think I'm gonna get this started while people trickle in. So thank you guys for coming. We have our last lecture here for Intro to Thermal Sciences and how they can help save the world. We're really excited for the panelists we've put together and to kind of hear some of their thoughts on how you guys can get involved in the future. And we titled today's panel, Combating Climate Change, Bringing the Lab, the Hill, the Field, and the Money, because we're going to need collaboration across scientists, politicians, engineers, and people that are doing startups out in the field, and those that have the money to actually make a change in the space that we're in. We have Bhargavi, who's working for Breakthrough Energy. Elise has started her own company called Aeroshield with some technology that's come out of the lab she was in. She recently graduated from MIT with. And then we have Professor Henry, who you guys have heard a lot about through this course. We're big fans of his work. We also took his class, so he's had a big impact on us in our passion for thermal science. And then Addison Stark, who's working at the Bipartisan Policy Center. So we're really excited to hear from them. And with that, we're going to turn it over to Bhargavi. I will stop sharing, and she can take over and just introduce herself and talk a little bit about some of her work.
Great, thanks, Cody. I will just share my deck real quick. Can you guys see my screen? Perfect. Good morning, everyone, or good afternoon, rather. As Cody said, I'm just going to talk a little bit about myself and my career and kind of how it fits into climate change, and then happy to answer questions later on. So a little bit about myself. I was born in India and lived there till I was 10, and then I moved to the US afterwards and have been here since then. And growing up, I always thought of myself as like just a typical tree hugger. Love the environment and haven't really thought about climate change. Hadn't really thought about climate change until I was 18 when I saw Al Gore's Inconvenient Truth. And, just seeing kind of the graphs in the movie and seeing how CO2 was going up and temperatures going up was completely terrifying. And it was my first time that, I truly thought about climate change and what it was as a problem, and still didn't think of it as something I should do in my career. Because when I was in high school and even in early college, I always thought I would be a doctor. And this is, thankfully that didn't happen, because that would have been the face of me looking at human bodies and blood and all of that stuff. So I realized in early college that probably wasn't going to be the career for me. And after majoring in chemical engineering at MIT, went to work for the energy industry, where I got to do a lot of cool things that were hands-on, did a lot of inspections in drums and reactors like this, learned how to be a good engineer then, but really felt like, thinking back to what I truly wanted to do, I've always wanted to make a difference. And so truly knew that at the end, climate change was a problem that I wanted to focus on and solve. And so, after spending a couple of years as an engineer in the energy industry, I started worked on starting a company with a friend of mine while in business school called Pico Energy. And what we were trying to do was focus on working in small villages in India initially. The plan was to, expand beyond that. And we looked at micro businesses, which are, small mom and pop shops in villages that weren't connected to reliable electricity with the grid. And so what we wanted to do is provide them with electricity and thereby increasing their revenue overall, because they'd be open longer and would be able to operate longer if it was a tailor shop, for example. And the idea was that by providing them with more revenue, they would be able to pay us back in terms of the fee that we would have incurred to provide them with the electricity in the first place using a solar system. it seemed like a great idea in person or in theory, but ultimately after doing a bunch of work, both remotely here in Boston and then also on the ground in India, my partner and I decided that ultimately it would be really tough to make this into a profitable venture, but it was an incredible experience. It was my first taste at the entrepreneurial lifestyle, and felt like that was my first real time that the startup bug bit me. While this wasn't ultimately successful as a company, I learned an incredible amount, really truly looking at what it takes to start a company, and ultimately what my next step would be. And that brings me to the current job that I'm at right now, where I work in venture capital. So a quick debrief on what venture capital does is if an entrepreneur like Sam in this case has a really great idea, for example, how to remove carbon from soil or put carbon into soil rather, and an innovative idea like that isn't going to be financed by a simple loan from a bank, which you might get if you were to start a franchise on McDonald's, for example. Because there's a lot more risk in using an idea like that and growing into a company. That's where venture capital comes in the form of Sue here, who gives Sam a bunch of money to pursue the idea and develop the technology, make a product, and then ultimately sell it to the market. And this enables Sam to continue building a business, and then Sue in return gets a portion of the business and then eventually profits for when Sam's business grows and gets sold or goes public. So that in effect is what I do for a living. I invest in companies that reduce greenhouse gas emissions, and they can be in any sector of the economy effectively. But before coming to joining my current job, in my mind, I thought climate change was effectively limited to electricity and maybe a little bit of buildings efficiency. And this, if there's one thing you take away from what you hear from me today, is just want to tell you, don't be like me, because the greenhouse gas emissions globally come from so many different places, and electricity is only a quarter of that. If you look at this chart, agriculture is almost contributes almost the same emissions as electricity, which when I first learned about that just kind of blew my mind. And so I just want to kind of put that out there today, is to think about, if you want to do something in the space, if you want to help reduce emissions in the world and fight climate change, I just wanted to highlight a bunch of other things that you can do, whether that's in agriculture, in transportation, buildings, or of course, electricity. There's, if that's what your passion is, like, definitely go for that. But if that's not, something that gets you excited, I just wanted to highlight a couple of other ideas that might be more interesting. For example, cement and concrete, world's most biggest man-made material by volume. And we're just going to be building more and more buildings in the coming years and decades as population grows higher. So how do we figure out how to make cement and then thereby concrete, which is takes up cement to make concrete? How do we figure out how to make that greener and in turn create less emissions? Additionally, air conditioning. I think most of you have experienced the ridiculously high temperatures this summer, and hopefully have relief from that from an air conditioner, but it also takes up a ton of electric power, and we need to figure out, as the world is growing and the middle class is getting more money on a global scale, they're gonna want air conditioning. And we need to figure out how to do that in an efficient way, and also something that would be with less emissions. Speaking of buildings, how do we figure out how to control buildings, make them smarter, so that instead of reacting to temperature changes, they can figure out predictively what's going on. Like, oh, today's going to be pretty cloudy. It's going to be kind of cold. So let's not kick on, the air conditioner as much. Can we use technology to help figure out how to make buildings smarter? And on the other hand, with agriculture, cows contribute a lot to methane emissions, mostly from burps. And so can we figure out a way to, reduce that, but still produce the same amount of meat that we need? And then on the other hand, can we figure out alternatives to meat that still taste like meat and just are as attractive as meat, but doesn't contribute to the emissions that come from there? Another area that could be super interesting is just farming. Can we figure out how to make fertilizer, within using microbes instead of putting in a bunch of ammonia to make fertilizer? Can we figure out how to capture carbon into the soil and enable that as a way to reduce just the CO2 that's in the atmosphere? Hydrogen, can we figure out how to make hydrogen from electricity instead of using natural gas for it, and use that to power our cars and other industrial processes? Trucking, in addition to electric vehicles in general, can we figure out how to move our stuff and our people with less emissions that are produced? Plastics, even though the actual landfill of plastics doesn't produce emissions in the short run, it does the actual production and incineration also produces emissions. Can we figure out a way to do that without them, piling up? And then lastly, but definitely not least, everything I've said so far was how do you reduce emissions from products that are already being made. But CO2 capture focuses on how do we take CO2 out of the air that is already kind of out there. And we need to do kind of all these solutions and more to help fight climate change. So just kind of, I gave you a couple of examples. Another good resource is Drawdown. There's a book out there, but you can also go to the website and they cover a number of solutions that go beyond just the obvious ones. So if you're thinking to yourself, I don't know if electricity generation is where I want to spend the rest of my life doing, you can find a ton of other ideas and start exploring them. And lastly, we need all hands on deck. This is a huge problem to solve in the coming years and decades, and not necessarily impossible though. And so we need your creativity, skills, and everything else to contribute in order to solve this problem. With that, I look forward to answering any questions later.
All right, thank you very much. And guys, remember to submit questions in the Q&A. You can submit them and we'll be answering them at the end, in addition to the ones we've pre-collected. All right, next up we have Elise.
Fantastic. Well, thanks, Cody. I'll just pull up some slides here. But I'll just kind of get started with an introduction. So my name is Elise Strobach, and I'm going to speak a little bit about, start off with kind of posing the problem that I think about in my startup, Aeroshield Materials. And it's buildings. So thanks to Bhargavi for really kind of previewing that this is one of the big challenges that we have. And if we take here a look at this thermal picture, what you see is kind of this thermal map, and where you see those hot spots, those losses coming through, whether you're talking about a hot building or a cold building, are those windows. And it turns out that buildings, as an overall energy use category, are consuming about 40%, are responsible for 40% of our greenhouse gas emissions. And of those emissions, windows, these thermal hotspots, are a huge problem. And in fact, every year in the United States, $40 billion in energy goes right out that window. And for a long time, people have looked at how to solve this. But if we think about this from a fundamental standpoint, from a technology perspective, that's not an easy challenge to solve. Our windows have to be really clear. They have to be insulating. We have to be able to afford them. We have to be able to install them and have them survive in our buildings. And so one of the ways that people have done this in the past is just using glass and multiple panes of glass. But if we think about ways that we can actually start to really solve this problem, one of the materials that's come to mind for researchers for a really long time is something called silica aerogel. And this is a nanoporous form of glass that's made up of tiny little nanoparticles that are all interconnected to create this really porous network of pores that are so tiny, they're on the order of nanometers. And that allows this material to be one of the most insulating materials in the world. But when we talked about what we need for windows, they have to be transparent. And these materials just haven't been before. And so it was actually my work during my PhD at MIT in mechanical engineering where really started to dive into this material and say, well, is there a way that we can make this useful for windows? And really start to get at that problem of having a new material set that helps us just make buildings better, both from a person living at home sitting next to my window on a cold day, but also from an energy perspective. If we can make the outsides of our buildings better, means that the kind of systems that we have to install can be cheaper, can be more efficient, and just better with the resources that we have in terms of how they perform and what happens to them over the course of their lifetime. And so the breakthrough that we really had in the lab at MIT was finding a way to make this super insulating material transparent. And so you can see a picture of it here with this really clear structure. But again, all this sheet of material is glass that's filled up with tiny little nanopores. And from an engineering perspective, there was a lot of time understanding that structure and how light and heat and radiation are traveling through this network. And how, as we make this network, we can make it differently to make those end properties even better. And I kind of staged this first because on my journey, this was a really pivotal turning point. For me, I'd always been kind of interested in clean tech space. And that was because I came from a really rural town in Wisconsin where, we saw and we interacted with nature every day. We had a garden, we really appreciated those things. So the other part was really appreciating, what I wanted to do with my life. I wanted to have an impact. I wanted to create something, a way to make people's lives better that could last beyond generations. And so that was really what led me into engineering in particular. Because at the time, I knew that I liked the environment and that kind of impact, but I didn't really know how to have that impact yet, other than I really like doing a lot of different things and, wanted to stay technical. I thought that was really interesting opportunities. And so I chose after high school, after talking to a lot of people in the industry and, just kind of trying to understand what kind of career trajectories there were. I chose to go into mechanical engineering at a school in Wisconsin because I really just wanted to learn how to solve problems. I didn't know what the key problem I wanted to solve yet was. So I said, let me go out and just learn how to learn and learn how to tackle tough problems. And the work that I did and the exposure that I had during my undergraduate degree led me to say, hey, I've found that there's a lot of problems to solve out there, but I don't feel like I have the skill set, the right tool set to really tackle them well. And from there, I said, well, let me look at graduate school. Let me get even deeper into a topic and really learn how to, go even more fundamental in my understanding, and then be able to use that as another tool set to solve these big problems. And so while I was in the process of that at MIT studying for my PhD, that was when we had the breakthrough of this material. And then it became about, now we have this really cool, fundamental understanding, this new material set, and we understand this nanostructure and how to make it do what we want. How do we actually turn that into impact? And it turns out that that's a whole other piece of the puzzle, is to be able to take those understandings and make them really useful. And that's one of the core, I feel like, core principles that you learn in engineering, is how to take this fundamental and really apply it in the way that kind of matches your passion. And so that led me to start this startup based around how do we now take this material from the lab and actually build out manufacturing of it to get this material inside of our windows and really have that thermal impact. And so now, actually just June of this year, started full-time on this company and are actually starting to build manufacturing. So I think one of the fun facts about me is that throughout my life, I've always enjoyed hobbies and making things. But, it started off in kind of some very different areas. So growing up, we did everything from learning a little bit of woodworking to learning how to sew and work with patterns. And what's interesting is I found all of those skills really useful, in addition to things that I tried out while I was in high school and during my undergraduate degree, like public speaking activities and, band and musical instruments. All of those things I think have really shaped me being able to learn how to learn and have this diverse set of skills to be able to apply it now. And I'll also just make a nod that it wouldn't be possible without working with really amazing people. And I have to say, clean tech space, technology space, and this environmental impact is filled with the most amazing people. They share a passion. They're really open. They understand that we're all rowing in this boat together, and they want to help each other get there. So that was another reason that really led me into the clean tech sector, because I just find that it fits my passion, and I can work with people with this same kind of broader impact and potential. And I'll just kind of briefly go over a little bit of the tech and how it got here, but happy to answer questions and even talk offline if there's questions or interest. Yeah, so in my journey, when we started to make this breakthrough with material, I think one of the interesting things is taking this kind of fundamental understanding of how to learn and how to do a deep dive into a topic and then drive innovation was really a common thread that I found in the research and in understanding how to commercialize this tech. So it actually started with, I'd already been working in the space in this material for about 3 years before we decided to look at the window application. And that meant that I had to jump in and actually learn about windows, because I knew the material, I knew aerogels, but I didn't understand what these aerogels needed to do to make our windows and our buildings better. So there was, kind of the fun of jumping in and learning a brand new industry. And I can point to a window now and find you where the logo is and tell you who made it and on what day that they made it now, which is a little bit nerdy, but it's also pretty exciting and a fun trick, when you're meeting new people and you ask them if they want to learn about windows. A huge crowd pleaser, I'll tell you. So that was a really interesting kind of thread that we put in parallel to all this fundamental understanding that we were doing. Looking at material properties. I got to handle these aerogels, they're a lot like glass styrofoam, and just really cool stuff. And we got to try new things and brainstorm ideas about them. And then we got to get into the details. When we started to make progress, then it became about, we're making this material better. Now, how can we make that material even better for impact? How do we make that application really utilize what we're working on? And so it's fed by technical data, but also by getting in the lab and working with it and just, questioning things and talking to people. And I kind of throw this picture up here because this layer of samples is the progress that we were able to make over 2 to 3 years. Taking this material, as I showed kind of those first pictures that aren't transparent at all, and being able to, as we move towards the right, to get to something that is now more transparent than glass and a really cool material set. And now, as I transition into this startup world, it's all about thinking of how do we translate those learnings to impact. So, getting them inside of a window and actually starting to build prototypes and putting them in demonstrations, which is just so exciting. And the real crux of it, what really excites us is that now we're working on taking this idea and really having an impact in the industry, which all that time I talked about learning the window market and the kind of people that are building in this space. Understanding how to craft our impact so that not only are we motivating people with thousands of dollars of money in their pockets because we can improve their energy efficiency and their comfort, but all the way to looking at, hey, if we could get this material adopted around the world, just for new windows that are going out, that's billions and billions of dollars in energy savings. And that's achievable within a shorter time span that we can then build on and have even more cumulative energy potential savings. And then look at other markets and do this in other ways. So I think in a lot of ways, this has become a really exciting path that I'm really passionate about. So happy to answer any additional questions, but I'll stop there for now.
All right, thanks, Elise. Professor Henry, you're up next.
Okay, can you hear me okay? All right.
Yes.
And I presume you can see my slides. So let me just tell you a little bit about my research first, and then I guess I'll give a few comments, a few words on what it is that I think you all, as what I consider the next generation, can contribute in particular. So my area of research really involves two things. Really from elementary school, I always had a passion for working on, at that time it was just called global warming. And I became passionate about it as soon as I learned what it was. And I was very much concerned that this could be the end of humanity if we don't figure something out. And so I went through school really always with a passion for that, but by the time I got to grad school, I ended up going in a different direction that was not directly applicable for working on climate change, and that was studying heat transfer at the atomic level. And this really was born out of some lingering questions I had from undergrad. I had some really rather deeply theoretical questions about what is temperature exactly, why does it have its own units, and what's so special about it. And that ultimately led me into a field of studying heat transfer and thermodynamics at a very very low dimensional scale and really the underlying physics of heat transfer. And so this figure on the left really just is a kind of symbolic figure that just represents some advances that my group has made in describing heat transfer from a fundamental level, the atomic level. What's listed here, this is basically experimental thermal conductivity, which is one key heat transfer related property. And then what our predicted values for the thermal conductivity are based on some theory that we developed. In short, what's special about this is just the fact that all of these different materials that are listed here, number one, could not be modeled accurately on their own, and let alone no one model was able to model all of them simultaneously. And so this is special because we have developed a different theory that explains all of them and gets them all right in one coherent framework. And so it's a very different physical picture for how heat transfer happens at the atomic level than what's existed previously. But after working on these kinds of things, I've really been able to, over the last, I would say, 6 or so years, develop a parallel lane of working on problems that are relevant for climate change. And so generally speaking, I now would probably introduce my group as we are interested in anything that we think actually will move the needle on climate change. We're bandwidth limited, and so there's a couple of main technologies I'll talk about now that are our main focus, one of which is the grid storage problem. So I think people have introduced it already. I saw a slide showing that basically electricity generation is responsible for about 25% of greenhouse gas emissions. If you imagine also electrifying transportation, that's another 14, 15% or so. The two together is about 40% of global carbon emissions. And so in theory, one technology, which is really the key, is energy storage, could enable all of those greenhouse gas reductions. And so this is probably one of the biggest single technological problems in terms of single technology that may have a tremendous impact. And there's what I like to call an international race going on. Not an international arms race, it's an international energy storage race. Everyone wants to figure out some way to do energy storage very cheaply. And so we have our incarnation of that, which is affectionately been called Sun in a Box. The way it works is one of the things that we've developed over the last few years that's, I think, a significant expansion of what we can do technologically is the ability to pump liquid metal at extremely high temperatures. So we can pump liquid metal well above 1,000 degrees C. 1,000 degrees C is where things start to basically glow white. And so in that temperature regime, it's really difficult to, number one, have even metals that are moving and have enough strength to hold their own weight and don't start to droop over time, let alone melt. Another big issue is corrosion. And so our approach has been to use ceramics. So it's a completely different class of materials, using graphite and ceramics to build thermal infrastructures that can survive and last for tens of years at extremely high temperatures. So the idea is you take energy and instead of storing it electrochemically like you do in a battery, you store it thermally. So you store it in a very cheap medium. In this case, in this figure, I'm showing it with liquid silicon. Silicon is basically sand where you take the oxygen off, and so it's very abundant on Earth. So imagine taking liquid silicon, you pump it, you heat it up by using electricity. That's excess electricity on the grid. Could come from any source, but we're specifically interested in storing renewable energy. Then you heat that liquid silicon up to a higher temperature, in this case 2400 degrees C. 2400 degrees C is about the temperature of a incandescent light bulb filament. So it's glowing white hot. And then you store the energy in a tank. You basically store it as hot liquid. When you now later want electricity back, you pump that hot liquid out of that tank and pump it through a converter. We sometimes call it a heat engine, but basically what it does is it converts heat back to electricity. In this case, usually it's done with a turbine with moving parts, and here we're actually doing the conversion with photovoltaics because we're so hot. So part of the reason we went so hot is that we actually do the conversion back with PV cells that are specially designed to convert the kind of light that's coming off of this infrastructure. So all these pipes and everything will be glowing white hot. These PV cells are very special in the sense that they have mirrors on the back. So most of the light is not able to be converted at high efficiency. So instead, you send it back to the infrastructure and preserve it. That's why we call it sun in a box, because it's like the sun is trapped inside of a box. The energy can't get out. The only energy is only able to get out through the above band gap portion of the light, the high frequencies that are able to be converted very efficiently. And so when the liquid metal goes through this piping network, it has some of its energy extracted, so it comes out cooler and it goes back into the cold tank. Now, these tanks, keep in mind, these tanks are ginormous. They're order 30 meters, 10 meters, 30 feet or so in diameter, and 30 feet tall. So they're very large tanks. They also take a very long time to cool down, and that's also part of how you preserve the energy. So this is one energy storage technology we're working on. We're very excited about it. We've got a bit of funding, and we're in the process of building a prototype in my lab. This is another technology that, sorry for the sound. This is showing us pumping liquid tin at 1400 degrees C. So you can see the liquid flowing here. Basically, we could have actually gone hotter than this. We stopped at 1400 just because we ran out of heater power, and we were really excited. We wanted to see what it looked like, so we cut a hole in the insulation. In doing so, a bunch of the light gets out, and we can't actually get hotter than this. But we've since pumped at 2000 degrees C. We've pumped much hotter than this before. And the second technology, now that we have this ability to pump liquid metal, the second technology we are just now getting started working on is methane cracking. In short, what we do, the way hydrogen is made today, as someone mentioned for agriculture, you need ammonia, and the way we get ammonia, you need hydrogen. The way you get hydrogen is you take methane and you oxidize it with water. So you take the oxygen and the water, react it with the methane, and you make CO2, and then the hydrogen gets let go, and you get hydrogen gas. Problem with that approach is you, of course, make a bunch of CO2. Instead, we'd like to do a different approach where you don't make any CO2. Instead, you take methane and just heat it up so hot that it falls apart. The molecule becomes unstable, and you get hydrogen gas and solid carbon. And so the idea with this is, you can imagine the simplest thing you could do is just put methane in a tube, keep oxygen away from the system, like maybe put it inside of a chamber so there's no oxygen around, heat it up. It's not going to combust. It'll decompose. You'll get solid carbon and hydrogen. The problem is the solid carbon is going to deposit on the walls of that tube. Let's say you're heating the tube from the outside. The problem with that is as the solid carbon deposits on the walls, very quickly it's going to choke the reactor. It's going to block the entire cross section of that tube, and you won't be able to run anymore. And then you'll have to cool it down, clean it out, start again. That whole sequence would be very expensive and very inefficient to do it that way. So instead, we are trying to use the fact that we can pump liquid metal to make a different type of reactor, which is called a bubble column reactor. So this is a large vat of liquid tin. Imagine blowing methane bubbles up through the tin, heats up to about 1400 degrees C inside the bubble. This reaction takes place, so you end up with a little tiny carbon particle inside the bubble and hydrogen gas. And so when the bubble reaches the surface, the carbon sits on top of the tin, liquid tin surface, because tin is much more dense than carbon is, so there's a density difference. So it's by buoyancy, it just phase separates and sits on top. And the hydrogen gas goes out through the top. Then you can do, because we can pump the liquid tin, we can move it around and we can separate it. And so we can separate the tin from the carbon, and we can use the tin to do what's called heat recuperation, where we can save a lot of the energy we put in to make it more economical. So this is exciting because this is potentially a route to making a cement replacement. So the bigger impact on carbon emissions is actually using the carbon here to make a construction material that can displace cement. So these are the two big technologies we're working on in my lab. I'm gonna, in the interest of time, I'm gonna just very briefly, we had a paper come out earlier this week. I'm just gonna briefly touch on, there are 5 grand challenges that we laid out that have to do with thermal energy. One has to do with energy storage. As I mentioned, we're working on an energy storage technology. Another one is cooling. So with all the air conditioning units that will be coming online, particularly in developing countries, it's expected that the global warming potential of refrigerants as they leak out of these AC units, and it's a small amount of leakage, but the global warming potential is huge, that they will become a significant fraction of global warming by 2050. Another one is industry, as also was mentioned earlier. Particularly cement, steel, aluminum, and hydrogen are some of the big industries that are responsible for CO2 emissions. And then there's this issue of rethinking cooling in terms of zonal heating and cooling. And if you think about lighting, you only turn on lights where you need it. But instead, when it comes to cooling, we cool the entire room, the entire volume. And so we could cut on the amount of energy required if we could figure out a way to actually just deliver the cooling where the people are and actually just cool the person rather than all the extra air around them. So this is another topic. And then there's also this idea of long distance transmission of heat. So if you look at this diagram, this basically shows all these sources of energy and where it ends up, and this all ends up being wasted heat over here. And so you can see from electricity production, there's a very large amount of waste heat. This waste heat happens to be right in the temperature regime that people want to be heated to. And so there's residential and commercial heating loads that could be met with a lot of this waste heat if we could move heat like we move electricity. We can move electricity and power lines. We're able to move lots of electricity through very little hardware. If we could figure out a way to do something similar for heat, we could utilize and repurpose this waste heat for actual heating loads. So this is another potential area where we could see some big gains. So I'll stop there, and any questions you have, I'd be happy to answer when we get to that part. Thank you very much.
All right, thanks, Professor Henry. So we've heard a lot from our people that are working in tech right now. Now I'm going to hand it over to Addison, who is still working in tech, but I think he's helping our friends on the Hill understand a little bit more about what's going on here.
Thanks, Cody. Also, I'm very excited to be here, especially with this panel of friends that I've known for a long time doing really incredible things. The nice thing about being the last person on a panel is the fact that you don't have to use slides. There's been a lot of information given to you from across the spectrum of some of the big challenges we're working on. But also importantly, having been somebody who is also a PhD in mechanical engineering, I got excited. I was like, maybe I'm going to campus. I'll just throw on an MIT sweatshirt instead and go with that. Is the fact that sometimes you don't have the opportunity to have slides or any sort of information to hand to people when you're talking about critical issues. So I also was at MIT, as I mentioned before. I grew up similar to Elise. I grew up on a farm in rural Iowa, where I was surrounded by the impact of the development of what was the first generation of so-called clean energy. So the development of renewable fuels, ethanol plants across the state of Iowa. And what I saw was the fact that this was not just being driven by technology development, but really it was being driven by policy. This idea that through the development of new technology, you're also able to drive economic development. New jobs is critically an important issue in this space. And ultimately, there are many different reasons that politicians decide to do things in the energy space. So what I decided to do after leaving my PhD at MIT, where I also worked on very interesting, fun reactor topics that for another day, you can go read my dissertation if you're oh so interested, is to go on into a job in the government. And actually, that's where I met Asha. Asha and I were both in an agency called RPE, the Advanced Research Projects Agency for Energy, which is focused on funding research in technical space all across energy. In particular, Asha and I have this shared background in thermal engineering, and while I was there, I was working on problems in the energy-water nexus, focusing a little different than what Bhargavi talked about before, which is I have a very controversial opinion is actually it's very low energy cost to make water. Water doesn't have an energy problem, but rather energy has a water problem. If we look at the use of water across the US, a lot of it goes into cooling power plants. So we were focusing on that issue, investing in advanced manufacturing to make it cheaper to build cooling towers and cooling heat exchangers for cooling power plants, or going towards actually not using water at all, but using air to cool power plants. And what I realized while I was at RPE is the fact that we were ultimately dependent on funding given to us by Congress. That at the end of the day, if we want to move the amount of money we need to move to address climate change, it's not anything one individual venture fund can do. While it's critically important what we're trying to do through investing a lot of private capital, what we really need to do is move public capital as well. You need to have policies to create markets. You need to have policies to bring in federal support of early risky technologies. And how do we take these technologies that Asha's working on, these things that, you know, to be frank, are still renderings on a slide? How do you actually prove out that first system, build the first 30-foot tank of molten metal? It's probably more money than Breakthrough Energy Ventures would like to do on any one project. And even though it's $1 billion fund, probably the first deployment is going to be on the order of that amount of money. So we need to think big. We need to think not just in the US, but around the world, as a lot of us, I'm sure in this class are coming from all over, is how do we mobilize politicians to care about these issues? And also, how do we communicate what is really interesting science and technology and fascinating to all of us? You know, I'm a big nerd, but you never are able to go through and explain anyone the fact. It's very difficult to explain to a congressman that they cannot legislate away the first and second law of thermodynamics, that they are fundamental. But instead, how do you work within thermodynamics? And one of the things that I would try to urge everyone is work on the technical problems, but always save time to communicate them with people and in a way where you're meeting in the middle. And I want to give a fun example of this and this will be the last little anecdote before we move to questions, because I know we're running a little late, is last fall I was up on the Hill. So by that, we meet up on Capitol Hill. I was sitting in the office of a congressman, and I know this is being recorded, so hopefully this doesn't get back to them. But I was talking to one of their staffers, essentially one of the people that ran their energy and environment work. And no congressman does it alone. They usually have a staff around 10 people. And the person that was running their energy and environment work did not have a technical background. Most people working on the Hill don't. And we were talking about how the electric grid works. So, okay, you generate electricity at a power grid. You have a transformer that takes that mid voltage, go to high voltage for long distance transportation, then you have a step down transformer. A lot of you probably have learned or have heard something about this. But fundamentally, somebody goes, I have a question. I was like, okay, we might probably some question about how a transformer works. They go, what is voltage? And when you realize you're at this point where you're sitting there, you're taking your keys, describing potential energy by dropping them as a way to describe physics that many of you have learned in high school, that means we're at a fundamental challenge of communicating and thinking about the technical challenges before us in addressing climate change. So I would urge everyone to think about how you talk to people who don't have the science background that you all intend to have, to talk about this issue and talk about the technology we need to address it, because ultimately it's one of the biggest challenges. And actually that's why I'm doing what I'm doing. So I'm excited to take on any questions you guys have. And I'm just, again, very happy to be here, Cody, so thanks.
All right, well, thank you guys very much. That was an awesome panel. It was great to hear all of your perspectives across the board and the different disciplines that you're working in. And I think each of you kind of gave great calls to action. I'm going to start with a question for Professor Henry real fast. And for those of you, I know you guys might have a class at 1. The session will be recorded, but you're welcome to stick around. We're probably just going to go a few minutes over so we can answer some questions, and we'll send out the recording afterwards. But the first question, I know Professor Henry was excited about this. You know, someone asked, I want to be a thermal scientist. what are the things that I should study in college, and what are some of the things I should start doing now to move down that path? Maybe you could answer it like, what does it mean to be a thermal scientist, and what does that even do?
Yeah, so thermal science is actually a rather broad field. It's primarily falls within the discipline of mechanical engineering, and depending upon where on the spectrum you fall in the science, it also could involve physics. So you could be somewhere and you could major in mechanical engineering, you could do applied physics or physics. Really depends on how sciencey you want to get. If you want to do more engineering, you definitely probably want to be more on the mechanical engineering side. But generally speaking, heat transfer is traditionally a mechanical engineering discipline. So most people you'll ever hear saying even the term thermal science will be people with a mechanical engineering background.
Great, thank you. So I think we had a great question that just came in through the Q&A that I'll just throw towards Addison. How did you branch your focus to policy from engineering? Did you work on policy in your PhD, or did you just start talking to Congress after?
This is actually a good question because there's a lot of ways to do this. So in undergrad, and I just answered a question, type it. So in undergrad, I was a math and chemistry major. I started as an engineer, but I decided I want to focus on the fundamental questions, much similar to Ashe. I had a lot of theoretical questions, kind of the whys. And then when I got to the end of my undergrad, I kind of realized, oh crap, I want to do something with impact. And how do I bridge into addressing that? So I did a master's program at MIT called the Technology and Public Policy Program in conjunction with doing a master's in mechanical engineering and then staying on and doing my PhD in mechanical engineering. So it actually was at MIT that I learned to be an engineer. I didn't work on policy issues during my PhD. I was focused on the technology I was developing, which was focused on using waste biomass to make liquid fuels through a route called gasification. That's a story for a different time. But fundamentally what happened was when I was working in DC is when I got more engaged in policy. And but that's not to mean that there aren't different ways to do it. You can get involved with policy issues as an undergrad. Getting involved with politics is important. Also, just there are ways that if you are in grad school, is finding ways to communicate your research. Again, I go back to communications a lot with policymakers is important. All the congressmen want to know about the next technology because they're interested in new companies being formed. So there's a lot of ways that you can do this, but fundamentally, I got involved because of just being exposed to it through a government agency. But I did have an interest, and I did a master's in it as well.
Awesome, thanks. So I kind of have a tag team question that'll be for Elise and Bhargavi. Elise, I was hoping maybe you could chat about what was it like to decide you're going to go and start and make a company, and maybe talk about this tech valley of death a little bit. And then Bhargavi, maybe you could comment a little bit more on what does it really look like for companies, people that are trying to put some technology together in the lab to translate it out into the real world. I guess just maybe you could talk about that pipeline together.
Yeah, certainly. So I can kind of start with a little bit of my perspective in it, which is, when I started my career, started undergrad and went into grad school, had no idea what entrepreneurship was or how to get there. And I think that in a lot of ways that was a really good fit for me to discover that was a passion after, because it really gave me the tool set that made me feel that this was a possible path, and as built upon it, really got invested in the tech and the potential that it had. And I think that in a lot of ways that passion really has to be there in one form or another to get you over that kind of valley of death. I guess I would say that there's a lot of trade-offs that you make to take a career path, particularly in the startup world. It's certainly not easy, and there's a lot of really unglamorous moments. But I think that, when you look at the potential we have and like the things that I'm doing and I'm learning, that kind of gets you over the hump. And I think that also you have to believe, particularly when it's a technology that you've developed and you're looking to commercialize it, when you come from that tech side, you really have to be the biggest advocate, because really, when you get a PhD, your goal is to be the foremost expert in that area, like arguably the foremost expert in that particular area that your thesis is around. And so nobody else is going to come in and take on the really tough work or stay up late at night, not only trying to answer questions about the tech, but figure out how to make people understand the value that you're creating, or maybe even understand that the value you think you're creating is not really what it is. And once you get that kind of motivation, I think it helps you get over a lot of the barriers, because to be honest, there are, and I'm sure Bhargavi can talk about them even more. But, I guess the first piece is that, really making sure that this is the right fit for you in terms of, like the problem that you want to solve and the skill set that you want to grow and develop. But I would say that the other thing that I found is, conservative person, research background, I like to look at all the facts and think through things very logically. And it can be really daunting to tackle all of the challenges that have to come. And so I think understanding why you're doing what you're doing really shows that you can get over those tough barriers. Like there's no amount of hard work. There's no limit to that. There's no limit to how much you can put in and really start to make things happen. So I guess I would say that it certainly is our real valley of death. And there are a lot of reasons that this might, I think other people would look at it and say there's failure potential. There's a huge chance that technologies like ours will fail for one reason or another. But I think that I've also redefined failure, that even if tomorrow we kind of had to, close up shop for whatever reason, the experiences that we've gained and kind of the impact, the attention we've drawn to this area and the discoveries that we've made in the field, we already count that as success. So I'd say that in a lot of ways there is failure for maybe metrics the way that people would traditionally define them, of saying, we didn't walk out of this maybe and make $1 billion as founders, but we did leave the impact, and that's kind of what drives us. So I would say that, again, in the clean tech space, that's a really unique community that kind of helps you get over those barriers. But I'll let Bhargavi bring her perspective as well.
Yeah, I just want to pull on that thread, Elise, that you talked about failure as a possibility. I think that's definitely a recognition. And for us, coming from, high school, college, grad school, failure isn't an option, or it's not looked down as a good thing. But in the startup world, you want to fail as quickly as possible and fail often, because the first avenue or the first solution you hit most likely will not be the right one that eventually will kind of lead you to success. And so just having that mental shift is so hard, but it's so necessary. Another thing, going back to Valley of Death, especially when we're looking at solving these breakthrough problems that truly have to have a big impact versus just small incremental solutions. You eventually want your solution to kind of have a huge impact, but it's important to start with smaller markets and smaller products so that you can start making money before you hit the really big stuff. So for example, if you're thinking about decarbonizing steel production, you don't want to immediately go for the biggest steel producers. You might want to start somewhere small that you can still kind of make something profitable before hitting the big kind of product and market. The other thing I would say is, focus on more smaller kind of capital versus having your first plant be $1 billion, because that's, there are going to be lessons that you learn. So if you can build something with, let's say, a couple of million versus hundreds of millions, you're going to learn a lot of lessons, and it enables you to, eventually have a much higher chance of success. And of course, going from lab, hopefully it won't require millions, but something a little bit less.
Great. Well, we have time for just one more. This one I'm going to open up. Hopefully each panelist can maybe give their thoughts here. I guess looking through a lot of literature, hearing people talk about this is going to be a really defining decade for climate change in the way that we invest in technology, the way we invest in education, the way that we just invest our time to move the needle on this. So I wanted to ask each of you, put on your coach. It's not just the fourth quarter. This is really the last minute of the fourth quarter that we have to make some real change. What would you say to this team here, to everyone that's here, and maybe we'll watch this later? What do we need to do, and what do we need more of to combat climate change, both now and in the future? What's something these students could do right now, today, and how should they be thinking about the next few years for them as they fit into solving this big puzzle that none of us could do alone. That's why we have this big panel here, because it takes a lot of different people with different backgrounds to solve this problem.
Can I go first? I would say my immediate and very strong opinion on this is we need a social movement. We need a revolution of sorts. I mean, what it is, if you look at the time scale it takes, or that it has taken in the past, to switch fuels from one fuel source to the next, you're talking about the 50 to 100 year time scale, and we don't have 50 years. And we need to effectively do an incomplete overhaul of our entire energy infrastructure. It's way bigger than switching fuels. And I'm very much of the opinion, I spent some time at RBE, like Addison said, and when I was there, it became clear to me that even if we had the technologies that hit all the metrics and all the performance and cost metrics today, it still wouldn't move fast enough. The market itself is not going to be a fast enough driver for these things to happen quickly enough. It'll be too little too late. And so we need a social movement, a revolution of sorts, where, and if you look at history, most, if not all, social movements have been led by the younger portion of the generation. And so we need you all to take up that challenge, to take up that, just like you see people protesting and upset about the killing of unarmed Black men by the police, and you see protests about Black Lives Matter. We need climate matters. We need a social movement that really galvanizes people to demand the stopping of the usage of fossil fuels. I can't emphasize strongly enough that I think so many people are under the misconception that renewable energy solves everything. I mean, just adding renewable energy does not stop climate change. You have to stop the usage of fossil fuels, which is a very different proposition. It's one thing to say, here, I'm giving you something new, eat this instead. It's a different thing to say, you cannot eat what you've been eating. Denying people the usage of the traditional infrastructure that they're used to, getting rid of currently profitable assets and stopping their usage is a very big proposition that will be met with very strong resistance, because you're asking people who make money on something to stop making money on it. And that will require the demand of the society, not asking, not negotiating. It will require the demand of the society that in order to survive on this planet, we demand that these things change. And so I think that there's no one better positioned than you all in the position you're in terms of figuring out what your next steps will be in your life and your career. But that is the level of energy, intensity. It's actually, I would even go further. It actually needs to be even higher and stronger than anything we've seen. If you expect to move the infrastructure that we have to something that we can sustain.
I think Asha had a great, call to arms, as one might call it. Asha's right that there's a big systemic challenge here, and I take a little more tempered view, kind of where I sit in DC. I work at a place called the Bipartisan Policy Center, as we might remember, which the way that I look at this is we also need to be able to create policy and to solve this problem that is resilient over different political swings. So to me, for those that have learned in their kind of intro government classes, it means we need 60 votes in the Senate to actually set law that will be resilient and work over the decades that are required. But that does not make it easier, but it does require thinking about how things are appealing to people across the political spectrum. Asha's right that it's the youth that usually leads these movements, but how do you think you action this? Both it's putting together a career, doing the things we've done. I see a question that was posed to us is wanting to focus on policy, but also recognizing how do you balance your technical interests with the need to think about things like political science and entrepreneurship. And you saw from everyone on this panel, we are all working across that spectrum of this problem, and it's good to learn about it all. Don't think about becoming an expert as an undergrad. that's a time to learn about a lot of different things. And I think that's an important thing, that if you're a scientist, take the classes in history, take the classes that get you out of your comfort zone. And also, you know, maybe a real actionable thing you can do now is start practicing your skills of persuasion on your grandparents. If they're not thinking about this issue in the same way you are, you know, when you see everyone at Thanksgiving and Christmas this year, start that conversation now, because then they're going to be a climate voter once they believe that their grandchild is actually building a career in this space.
Yeah, I co-sign on everything that Asha and Addison said. The other thing I would say is think about, you know, on your own personal kind of power, how you can use that to pick certain products or go about certain ways of life. You know, the stuff that you can do can make a big difference, not only for yourself, but also then, you know, to Addison's point, educating your family, your friends on how you can make certain choices, whether that's, you know, demanding cleaner power to be supplied to you, or using less fast fashion, or, you know, thinking about your intake of, you know, meat, not necessarily to, you know, eliminate it entirely, but can you reduce it a little bit? Can you substitute it with other things? And then do that yourself, and then kind of, you know, talk to people in your community about it as well.
Yeah, I think from my perspective, all these pieces I think are right on the money. You know, I think as an engineer, we think about this as a problem to solve, and it's easy to say from the tech side, analyze it and say this is what needs to happen to make change. But turns out that people are part of every aspect of that decision. And so I think there's a need to kind of put on our empathy hats, right? And understand why this hasn't happened, why policy hasn't changed, why people are resistant, and say, you know, maybe it isn't founded in good, strong facts. Maybe it's perception, but people are acting on those perceptions. And I think to implement the problem, you know, to implement solutions to these problems, we have to understand the kind of fears and worries that people are having, and find ways to correct those. And I think that there are a lot of mechanisms to do it. And I think that, you know, from my journey, you know, I'm definitely not good at everything. And the way that I felt that I could make a change was to come at it from the tech side and to understand, you know, what are the barriers to a new tech? But if you're trying to change policy, if you're trying to change research, if you're trying to change, you know, funding for this, we all have unique sets of skills and can tackle different aspects of that problem. And I think that there is this need for everybody's diverse experiences to come together, because we all have to give a little. And I think it starts in our personal lives and it builds to what we can do. And we all as individuals have a lot more power. I mean, even just going back, you know, as Bhargavi mentioned, to family, you know, all the way to local policy and government, Addison and Ashe were saying, all these pieces have to come together. And I think there's also a piece where, you know, it can be really overwhelming, but, you know, we can't let the fear of not doing everything stop us from doing everything we can right now. And I think that builds in a really powerful way.
All right, well said. It feels anticlimactic, not all in a room clapping together, but I think I would speak for everyone here. You'd have a huge roar of applause. So on behalf of me, the students, the rest of the co-teachers, thank you guys so much for coming out today to talk and share your perspectives, talk about your careers, and just give your honest thoughts on what everyone needed to hear for the future, what they need to do. So thank you guys again. To wrap this up, thank you, class, for making this semester really, really enjoyable. I think all the co-teachers had a lot of fun giving you guys just an intro to thermal sciences, you know, what they can do, what the power of them are, but showing you how they fit into this broader problem of climate change. Some things you guys could do next, I would just encourage you all to look up some of the local programs you guys have at your schools, at your colleges. MIT has something called MITES that they run in the summer. Do things like this, HSSP, and learn about some of these different topics that you have. I'll throw a quick shout out to the MIT Water Scholars Program. It's a program where you get to partner with some graduate students at MIT, and they'll take a deep dive into research with you. You guys will get to do a presentation later. This will run next spring, so you can check out their website to see what's going on there at MIT Water. And I think it'll probably have more of a sustainability focus moving forward, not just things on water. So with that, we're gonna end this panel. Thanks again to our panelists. Thank you, students, for coming in and listening. And thank you all for making this a great semester. All right, have a good summer, guys.
Thanks, Cody. Had a great time.
Thanks, everyone. It was really good. Powerful.
Yeah, thank you.
Thanks
This
for
was
that.
fantastic.
Yeah, thank you.